Welcome! Today, we'll explore LeetCode problem number 2100, find good days to rob the bank. This problem challenges us to identify days with optimal conditions for a low-risk robbery, based on a given security pattern over several days. Stay tuned as we break down the problem and solve it step by step. This problem requires us to determine the best days to rob a bank based on the bank's security measures. These measures are represented in a list called security, where each value corresponds to the security level on a specific day. The challenge is to find all the days that qualify as good days for a robbery. A day is considered good if, for the K days leading up to it, the security measures are non-increasing, meaning they either decrease or stay the same, and for the K days following it, the security measures are non-decreasing, meaning they either increase or stay the same. Mathematically, this means that for day I, the values in the K days before it should form a non-increasing sequence, and the values in the K days after it should form a non-decreasing sequence. Using these rules, we need to identify and return all such days, ensuring that the result is provided in increasing order of their indices. In addition to the security array, we are given an integer k, which determines the number of days we need to check before and after a particular day. If k is 0, no checks are required, and every day is automatically a good day. The output for this problem is a list of integers representing the indices of all days that qualify as good days for robbery. To understand this better, let's look at an example. Consider the input security equals 5, 3, 3, 3, 5, 6, 2, and k equals 2. For day 2, the k equals 2 days before it are 5, 3, 3, which form a non-increasing sequence. This means the security measures either stayed the same or decreased over these days. Now, we also need to check the k equals 2 days after day 2. The k equals 2 days after day 2 are 3, 3, 5, which form a non-decreasing sequence. Since both conditions are satisfied, day 2 qualifies as a good day. Similarly, for day 3, the k equals 2 days before it are 3, 3, 3, which are non-increasing, and the k equals 2 days after it are 3, 5, 6, which are non-decreasing. This means day 3 also qualifies as a good day. No other days in this example meet the criteria. In another example, if security equals 1, 1, 1, 1, 1, and k equals 0, every day is automatically a good day because no checks are needed before or after each day. Thus, the output in this case would include all the indices 0, 1, 2, 3, 4. Now, consider an example where no days qualify as good. If security equals 1, 2, 3, 4, 5, 6, and k equals 2, there are no days where the k equals 2 days before are non-increasing and the k equals 2 days after are non-decreasing. For instance, on day 2, the k equals 2 days before are 1, 2, 3, which are increasing, so the condition for non-increasing days is not satisfied. Similarly, for other days, at least one of the conditions fails. Hence, the output is an empty list, as no days meet the criteria. These examples illustrate how the criteria for a good day depend on the specific values in the security array and the value of k. To wrap up, there are several edge cases to consider when solving this problem. If k equals 0, every day is trivially a good day since no checks are required. When all values in the security array are the same, every day is a good day as long as k is valid. For small arrays, special cases like security equals 1 or security equals 2, 2 need to be handled correctly. On the other hand, for very large arrays, where len security reaches up to 100,000, the solution must be efficient to handle the input size within the time constraints. Additionally, when k is large, approaching half the size of the array, it becomes more difficult for days to meet the criteria, and in some cases, no days may qualify as good. These edge cases highlight the importance of designing an efficient and robust solution for this problem. To solve problem number 2100, the goal is to identify all the good days to rob the bank. A day qualifies as good if, for the time days before it, the security levels are non-increasing, and for the time days after it, the security levels are non-decreasing. The input includes an array security, which represents the daily security levels, and an integer time, which specifies the number of stable days required on both sides of a potential robbery day. A straightforward approach is to iterate through each day in the security array and verify these conditions. For a given day I, we check whether the time days before it form a non-increasing sequence and the time days after it form a non-decreasing sequence. If both conditions are satisfied, we can add that day to our result. This brute force approach involves checking all days from index time to anytime 1, ensuring that the edges of the security array are not accessed out of bounds. The brute force solution, while intuitive, has significant drawbacks in terms of efficiency. Verifying the conditions for a single day takes time operations, and since there are n days in total, the overall time complexity is n** time. In the worst case, when time is nearly equal to n, this approach becomes n². Such a complexity can be impractical for large inputs, especially since n can go up to 100,000 as per the problem constraints. To address these performance issues, we can adopt an optimized strategy using prefix and suffix arrays. The key insight here is to pre-process the security data, allowing us to efficiently determine whether a given day meets the conditions without recalculating the sequences repeatedly. Specifically, we can use two auxiliary arrays, non-increasing to count consecutive non-increasing days ending at each index, and non-decreasing to count consecutive non-decreasing days starting at each index. This pre-processing step enables constant time checks for each day, making the solution far more efficient. The optimized approach involves two main steps: pre-processing the data and validating the results. First, we create the non-increasing and non-decreasing arrays. To build non-increasing, we iterate through the security array from left to right, incrementing the count at each index if the current day's security level is less than or equal to the previous day's. Similarly, to build non-decreasing, we iterate from right to left, incrementing the count if the current day's security level is less than or equal to the next day's. Once these arrays are populated, we can evaluate each day from index time to anytime 1. For a day to qualify as good, its non-increasing and non-decreasing values must both be greater than or equal to time. If these conditions are satisfied, the day is added to the result list. The pre-processing step and the validation step each take linear time, resulting in an overall time complexity of n. This is a significant improvement over the brute force approach, making it suitable for large inputs. The optimized strategy using prefix and suffix arrays is the chosen solution due to its efficiency and scalability. By pre-processing the security data, we reduce the time complexity from n² to n, which is crucial for handling the upper limit of the problem's constraints. The key insight lies in leveraging the sliding window property of the problem. Instead of recalculating sequences for every day, we pre-compute the number of consecutive valid days, enabling constant time checks for each potential robbery day. This approach does involve some trade-offs. While the brute force method is simpler to implement, it is computationally expensive for large arrays. The optimized solution, on the other hand, requires additional space for auxiliary arrays and slightly more complex logic, but the performance gains make it the only practical choice for large inputs. With n up to 100,000, this linear complexity ensures the solution remains efficient and scalable for all valid inputs. The problem focuses on identifying good days to rob the bank based on a sequence of security levels over several days. A day qualifies as good if the security levels have been non-increasing for a specific number of days prior to it and non-decreasing for the same number of days following it. The challenge lies in efficiently determining these days given the constraints. First, we need to validate the input. If the length of the security array is less than 2* time plus 1, the task becomes impossible because there aren't enough days to satisfy the conditions. In such cases, we directly return an empty list. This simple check prevents unnecessary computation for invalid inputs and sets the foundation for the algorithm. Once the input is validated, the next step is to calculate two arrays, the non-increasing prefix array and the non-decreasing suffix array. The non-increasing array helps us track how many consecutive days, up to a maximum of time, the security levels have been non-increasing before each day. To build this, we traverse the security array from left to right. If the current day's security level is less than or equal to the previous day's, we increment the value in the array. Otherwise, the sequence breaks, and we reset the value to 0. Similarly, the non-decreasing array tracks consecutive days of non-decreasing security levels after each day. This time, we traverse the array from right to left. If the current day's security level is less than or equal to the next day's, we increment the value. Otherwise, we reset it to 0. With these two pre-computed arrays, we efficiently capture the qualifying sequences of days around each index. After constructing the prefix and suffix arrays, we proceed to identify the good days. This is done by iterating through the security array, starting from index time and stopping at end time 1. At each index, we check if the corresponding values in the non-increasing and non-decreasing arrays are both greater than or equal to time. If they are, the day satisfies both conditions, and we add its index to the result list. Finally, the algorithm outputs this list of indices as the solution. By leveraging the pre-computed arrays, we avoid redundant calculations, ensuring that the algorithm is both efficient and concise. Analyzing the complexity of the solution, the time complexity is O(n), where n is the length of the security array. We make 3 linear passes, one to compute the non-increasing array, another for the non-decreasing array, and a third to identify the good days. The space complexity is also O(n), as we use 2 auxiliary arrays to store pre-computed values. Considering edge cases, if the security array has fewer than 2 time plus 1 days, no days can be good. For uniform security levels, all days might qualify as good depending on the time parameter since the conditions are trivially satisfied. On the other hand, strictly increasing or decreasing security levels result in no good days, as one of the required conditions will always fail. These considerations ensure our solution is robust and handles a variety of scenarios. To better understand the algorithm, let's go through an example. Consider the input security equals 5, 3, 3, 3, 5, 6, 2, with time equals 2. First, we compute the non-increasing array, which becomes 0, 1, 2, 3, 0, 0, 0. This shows how many consecutive non-increasing days precede each index. Then, we calculate the non-decreasing array as 0, 0, 0, 0, 1, 2, 0, representing the consecutive non-decreasing days following each index. Now, we check 4 good days. At index 3, both arrays have values greater than or equal to time, making it a valid day to rob the bank. The result is 3, which we return as the output. This example illustrates how the algorithm combines pre-computed values to efficiently solve the problem. This solution efficiently calculates the good days to rob the bank using 2 auxiliary arrays, non-increasing and non-decreasing. The input security represents the daily security levels, and time specifies the minimum number of days to check before and after a given day. First, we handle the edge case where time is 0. In such cases, all days are considered good days, and we return a list of all indices. Next, the non-increasing array is computed to track how many consecutive non-increasing days exist up to each day. This is done with a simple loop that checks if the current day's security level is less than or equal to the previous day's security level. Similarly, the non-decreasing array is computed in reverse order to count consecutive non-decreasing days starting from each day. Finally, the main loop iterates over the days that could potentially be good, from time to end time. For a day to qualify as good, it must have at least time non-increasing days before it and time non-decreasing days after it. If both conditions are met, the day is added to the result list good_days. This approach ensures that the solution runs in O(n) time, as we make a single pass to compute each of the 2 auxiliary arrays and another pass to find good days. The algorithm is space efficient, as it uses only 2 additional O(n) arrays. This makes it well suited for the problem constraints. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, gooddays_to_robBank, takes 2 inputs, an array called security and an integer time. The goal is to find all the days where it's safe to rob the bank based on the conditions provided. First, we determine the length of the security array and handle a special case where time is 0. If that's the case, every day is considered a good day, so we add all indices from 0 to n1 to a list and return it. Next, we introduce 2 arrays, non-increasing and non-decreasing, to help track the number of consecutive days where the security values are non-increasing or non-decreasing. These arrays will allow us to efficiently check the required conditions for each day. We then calculate the non-increasing array by iterating from left to right. If the current day's security is less than or equal to the previous days, we increment the value in the non-increasing array. This tracks how many consecutive days up to the current day satisfy the non-increasing condition. Now, we calculate the non-decreasing array by iterating from right to left. If a day's security value is less than or equal to the next day's, we increment the value in the non-decreasing array. This way, we can track the number of consecutive days from the current day onward that meet the non-decreasing condition. With both helper arrays ready, we proceed to identify the good days to rob the bank. We iterate through the days, starting from time and ending at end time. For each day, we check if the values in the non-increasing and non-decreasing arrays at that index meet or exceed the time threshold. If both conditions are satisfied, the day is added to the good days list. Finally, once all potential good days are evaluated, the method returns the list of these days. This approach ensures that we efficiently find all valid days without redundantly checking conditions for every possible day. To solve this problem, we start by initializing a few variables. The length of the security array is 7, and we create two helper arrays, non-increasing and non-decreasing, both initialized to all zeros. These will help us track the number of consecutive days with non-increasing and non-decreasing security levels, respectively. Additionally, we initialize an empty list good_days to store the final output. The first major step is to calculate the non-increasing array. For each day starting from the second day, we compare the current security level with the previous day. If the current day's security is less than or equal to the previous day's, we increment the value in non-increasing by adding 1 to the previous day's value. For example, on day 1, since 3 is less than or equal to 5, we set non-increasing 1 to 1. The process continues, and we only update the array when the condition holds. By the end of this step, the non-increasing array is partially updated, showing the number of consecutive non-increasing days up to each index. After finishing the calculation for non-increasing, the final array is 0, 1, 2, 3, 0, 0, 1. Next, we focus on calculating the non-decreasing array, which is done by scanning the security array from right to left. Starting at the second to last day, we compare the current day's security level with the day after it. If the current day's security is less than or equal to the next day, we increment the value in non-decreasing by adding 1 to the next day's value. For instance, on day 5, security 5 is less than or equal to security 6, so we set non-decreasing 5 to 1. This process continues for each day, updating the array whenever the condition is satisfied. By the end of this step, the non-decreasing array reflects the number of consecutive non-decreasing days starting from each index. Notice how the values build up as we move further left, especially for days where the security levels remain steady. Now that we have both non-increasing and non-decreasing arrays, we can determine the good days to rob the bank. These are days where the number of non-increasing days before the current day and the number of non-decreasing days after the current day are both at least equal to the given time. Here, we check indices from time to end time, which in this case means indices 2 to 4. At index 2, both conditions are satisfied because non-increasing 2 is 2 and non-decreasing 2 is 4, both greater than or equal to time. Therefore, we add day 2 to the good_days list. Similarly, at index 3, the conditions are also met, so we add day 3 to the list. However, at index 4, the non-decreasing value is less than time, so we skip this day. After processing all relevant indices, the final result is that days 2 and 3 are good days to rob the bank. Let's now consider another example where security is 1, 1, 1, 1, 1, and time is 0. First, we initialize the variables. The length of the security array is 5, and since time is 0, there's no need to calculate the non-increasing or non-decreasing arrays. This is because when time is 0, every day is automatically a good day to rob the bank, as there are no restrictions on the number of consecutive non-increasing or non-decreasing days. Therefore, the output list good_days contains all the indices 0, 1, 2, 3, 4. This edge case highlights how the solution handles scenarios where the constraints are minimal, making all days valid. In this example, security is 10, 5, 1, 5, 10, and time is 1. As usual, we start by initializing the variables. The length of security is 5, and we create the non-increasing and non-decreasing arrays, both initialized to zeros. We also initialize an empty list good_days. The first step is to calculate the non-increasing array. Starting from the second day, we compare each day's security with the previous day. If the current day's security is less than or equal to the previous day's, we increment the value in the non-increasing array. For example, on day 1, 5 is less than 10, so non-increasing 1 is set to 1. Similarly, at day 2, 1 is less than 5, so non-increasing 2 becomes 2. On days 3 and 4, the condition is not satisfied, so no updates are made. At this point, the non-increasing array becomes 0, 1, 2, 0, 0. Next, we calculate the non-decreasing array by iterating through the security array from right to left. Starting at day 3, we compare each day's security with the following day. If the current day's security is less than or equal to the next day's, we increment the value in the non-decreasing array. For example, on day 3, 5 is less than or equal to 10, so non-decreasing 3 becomes 1. At day 2, 1 is less than or equal to 5, so non-decreasing 2 is updated to 2. Days 1 and 0 don't meet the condition, so their values remain unchanged. The final non-decreasing array is 0, 0, 2, 1, 0. Finally, we check indices from time to end time, which in this case are indices 1 to 3. At index 1, the non-increasing value is sufficient, but the non-decreasing value is not, so we skip this day. At index 2, both values meet the condition, so we add day 2 to good_days. Index 3 is skipped because the non-decreasing value is less than time. The result is that day 2 is the only good day. The final output for this example is good_days equals 2. This result highlights how the algorithm identifies days that satisfy the conditions for both non-increasing and non-decreasing sequences. By carefully iterating through the security array and leveraging the pre-computed helper arrays, we efficiently determine the good days to rob the bank while adhering to the given constraints. To analyze the time complexity of our solution, let's break it down into 3 main steps. First, we calculate the non-increasing array. This requires iterating through the security array from left to right, and for each index, we check if the current value is less than or equal to the previous one. This operation involves a single loop across the array, making it O(n). Next, we compute the non-decreasing array, where we perform a similar operation but traverse the array from right to left. Again, this requires a single loop and is O(n). Finally, we identify the good days by iterating through the valid range of indices and checking the conditions for both non-increasing and non-decreasing. This step also involves a linear traversal, making it O(n) as well. Each of these steps is independent, so their complexities add up linearly. By combining the complexities of all 3 steps, we get O(n) plus O(n) plus O(n), which simplifies to O(n). This means the overall time complexity of the solution is O(n), where n is the length of the security array. Now, looking at the space complexity, the main contributors are the non-increasing and non-decreasing arrays. Each of these arrays has a size equal to the length of the security array, which is O(n). These arrays are used to store the counts of non-increasing and non-decreasing days, respectively. Thus, their space requirements are linear. The third contributor to space complexity is the good_days list, which stores the indices of the good days. In the worst case, all days in the security array could potentially be good days, meaning the size of this list would be at most n. This also contributes O(n) to the space complexity. Variables like I used in the loops require negligible space, or O(1). When we sum up the space requirements of these components, the non-increasing array, the non-decreasing array, and the good_days list, we get O(n) plus O(n) plus O(n), which simplifies to O(n). Therefore, the overall space complexity of the solution is O(n). To better understand the efficiency of this approach, let's compare it to a brute force method. In a naive approach, for each day in the security array, we would manually check the time days preceding it for a non-increasing trend and the time days following it for a non-decreasing trend. This would involve an outer loop iterating over each day, which is O, n, and an inner loop checking time days, which is O, time. As a result, the time complexity of the brute force approach would be O, n asterisk time. On the other hand, the optimized solution avoids these nested loops by pre-computing the non-increasing and non-decreasing arrays in linear time. This ensures that each index is processed only once, reducing the time complexity to O, n. This efficiency gain becomes especially significant when time is large, as the optimized solution scales linearly with the size of the input. When we analyze the algorithm in terms of best, average, and worst cases, we find that the time complexity remains consistently O, n, regardless of the input. In the best case, the algorithm must still process the entire security array to compute the non-increasing and non-decreasing arrays. Similarly, in the average case, the entire array is processed to identify potential good days, and the complexity remains O, n. In the worst case, such as when all elements in the array are equal, the algorithm still performs the same operations with no additional overhead. This uniformity in performance makes the solution highly efficient and scalable, as it processes the input in linear time in all scenarios. When solving this problem, there are several common mistakes to watch out for. One major issue is not properly handling edge cases for the time variable. For example, if time is greater than or equal to the length of the security array, it's impossible for any day to meet the conditions for being good, and failing to account for this can lead to incorrect results. To address this, always validate edge cases where time exceeds or equals the array's length. Another frequent mistake involves misinterpreting the definitions of non-increasing and non-decreasing sequences. Remember, these sequences allow for equality, so, for instance, a sequence like 5, 5, 4 is valid for non-increasing. Additionally, using inefficient pre-computation methods, such as nested loops, can lead to an O, n squared, time complexity, which may not work for larger inputs. Instead, you should use two-pass prefix arrays to achieve a more optimal O, n, solution. Finally, off-by-one errors in indexing are another challenge. These errors occur when the boundaries of the time window are misplaced, leading to missed valid days or the inclusion of invalid ones. Carefully ensure that the window size matches the value of time and that indices are properly aligned to avoid such issues. Another common oversight is ignoring the constraints on the time variable, particularly when time is 0. In this special case, every day automatically qualifies as a good day since there are no days before or after to evaluate. Accounting for this edge case can save unnecessary calculations and ensure correct logic. In interviews, this problem highlights important insights. One key pattern is recognizing that this problem revolves around identifying monotonic subarrays, which is a common theme in sliding window and prefix/suffix problems. Mastering this pattern can help you tackle similar problems more effectively. Additionally, interviewers often focus on optimization, so it's important to demonstrate an efficient O, n solution using a two-pass approach with prefix arrays, as a naive O, n squared approach will likely fail for large test cases. Be prepared to discuss edge cases in detail, such as when time is 0, when time is greater than or equal to the length of the array, or when all security levels are identical. Finally, you might encounter follow-up variations, such as finding the first good day or modifying the problem to allow unequal time values before and after each day, so keep these potential changes in mind. This problem also shares connections with several related problems that you may find helpful. For instance, in LeetCode 238, product of array except self, prefix and suffix arrays are used to solve the problem without directly iterating over the product. Similarly, LeetCode 724, find pivot index, relies on prefix sum logic to find a balance point in an array. In LeetCode 905, sort array by parity, the focus is on partitioning elements under specific constraints, and LeetCode 581, shortest unsorted continuous subarray, challenges you to identify the smallest subarray that needs sorting. Exploring these problems can deepen your understanding of array manipulation and prefix/suffix techniques. When it comes to alternative approaches, the naive brute force method involves checking the time days before and after each day to determine if the conditions are satisfied. However, this approach has a time complexity of O, n asterisk time, making it inefficient for larger inputs. While simple to implement, it's not scalable. A more efficient strategy involves using two-pass prefix arrays. Here, you pre-compute two arrays, non-increasing and non-decreasing, to store the number of consecutive days that meet the conditions on either side of each day. This method achieves O(n) complexity for both pre-computing and checking, making it a scalable yet slightly more complex solution. Another efficient approach is using a sliding window to dynamically track non-increasing and non-decreasing sequences. This method involves maintaining a window of size time as you traverse the array, updating the window dynamically to check the conditions for each day. The sliding window approach also achieves O(n) complexity, and for some candidates, it may offer a more intuitive implementation compared to prefix arrays. However, it requires careful handling of window boundaries, as small mistakes in managing the window size or its indices can lead to incorrect results. While it may feel simpler for certain cases, the dynamic nature of the sliding window can make it slightly harder to debug than the prefix array approach. Both methods offer efficient solutions, so choose the one that best aligns with your understanding and the requirements of the problem. Great job! We've successfully tackled LeetCode problem number 2100. Remember the importance of prefix-suffix patterns and how they can simplify complex problems. Keep practicing, and we'll see you next time for another exciting coding challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!